The number of poles in an electric machine. This talk is about the number of poles in an electric machine. It's a personal view, although it is generously hosted by JSOL. It does not represent JSOL in any way. In these videos, I don't use animation or colored lights. I'm trying to encourage calm reflection on rather abstract topics, even though this is a very practical subject. And of course, I think it's important to enjoy the rich language of our subject. The number of poles in an electric machine. This means, of course, the number of magnetic poles, or north and south poles. In times gone by, one of the conceptions of magnetism involved particles, if you will, of north or south polarity sitting on the surfaces of magnetized bodies. What was remarkable was that the numbers of north and south poles were always equal, and it was impossible to find an isolated pole of either polarity. Today, in electric machine engineering, we take this for granted, and the principle of balance, which I've just mentioned, is embodied in Gauss's law, and therefore in Maxwell's equations. So we tacitly assume that finite element programs like JMAG include that principle in doing what they do, and no questions are asked. But the division of machines into homopolar and heteropolar is a topological distinction of great importance, particularly in the context of new inventions with axial flux and linear machines and all kinds of variants. Let's start with this sketch of the rotor of a homopolar inductor alternator. It has 3 poles at one end and 3 at the other. The poles at this end are all north, and the poles at the other end are all south. Considering just one end, is it possible to have an odd number of poles? Of course it is, in this configuration, provided that we count norths and souths. 2 times an odd number is an even number, and Gauss's law is satisfied. Now, if we add an armature coil, we can see a bit better what is going on. The north pole at this end passes flux through the coil, which is in a position of maximum flux linkage. This flux must return to a south pole somewhere at the other end, but in doing so, it must not pass back through the coil. That's the reason why the south poles are all displaced 60 degrees or 180 electrical degrees, as we can see. There are 2 really awful consequences. One is that the coil is linking less than half the flux which it could link if the north pole flux were threading it all along its length. The other is that in finding its way from the north to the south through the magnetic structure, the flux must flow in several places in the axial direction. Laminating the stator will not prevent eddy currents in the plane of the laminations, so the eddy current losses will be a problem. On the rotor, the flux is modulated by the passing slots, so there will be eddy current losses on the rotor as well. Very few machines are made in this configuration, but a notable exception is the hybrid stepping motor. The magnetization is provided by a permanent magnet magnetized in the axial direction between the rotor pole assemblies, and the number of poles is much higher than 3. Historically, two ends of this rotor were brought together in an imbricated structure, two of these. And an example is this claw pole arrangement used in the Sturmey-Archer bicycle generator, where the magnet is magnetized in a heteropolar fashion with 20 poles, while the stator has imbricated pole pieces surrounding a single coil winding. The winding is clearly homopolar, while the magnet and the pole pieces are heteropolar. It's an interesting question as to whether this construction could work as a motor. It certainly wouldn't be self-starting. Today we find a similar arrangement in automotive alternators, which of course are made in the millions. In these, the single coil is a homopolar field winding excited with DC, and it is rotating. The magnet is replaced with a more or less conventional AC stator with a three-phase winding. So you have an electrically excited AC generator. Machines of this type date back to the 1880s, and some very large ones were made even then, up to several hundred kilowatts, driven by water wheels or early steam turbines. So far, these machines have been partly homopolar and partly heteropolar, but let's move on to consider pure heteropolar machines, which generally have a north-south, north-south, north-south magnetization in a 2D cross-section that remains the same the whole length of the machine. We can consider the main question, that is, the number of poles or pole pairs. In AC machines, the frequency is equal to the number of pole pairs times the number of revolutions per second. From the early days, the conflicting requirements of this equation were apparent. The smallest possible number of pole pairs is 1, while in AC distribution systems the frequency needed to be at least 40 Hz and maybe 50 or 60 Hz or more to avoid lamp flicker, especially with incandescent tungsten filament lamps, which is what was used for a century or so. Westinghouse even started with a frequency of 133 Hz. This is one reason why steam-powered generators are nearly always built with 2 or 4 poles, running at speeds of 3,000 or 3,600 revs per minute, 2-pole, or 1,500 or 1,800 revs per minute, 4-pole. Water wheel generators could not run at these speeds, but at much lower speeds of the order of 90 revolutions per minute. Therefore, they need a larger number of poles. For example, the large hydro generators at Itaipu in South America run at 90.9 revolutions per minute with 66 poles. One of those rotors weighs nearly 1,800 tons, by the way. When the speed goes down, the torque must go up in order to maintain the same power output. So the large water wheel generators have large rotor diameters of the order of 3.5 meters, something like 3 times the diameter of a steam turbine generator rotor. Now, for many years, AC machines in normal industrial use were predominantly 4 and 6-pole machines with smaller numbers of 2-pole, 8-pole, and other pole numbers. The numbers of slots per pole was generally quite high, let's say between 3 and 12. So, for example, you might find a domestic refrigerator induction motor with 2 poles and 24 slots, 12 slots per pole. In larger polyphase machines, 4 poles and 36 slots was a popular combination, having 9 slots per pole. The coil span would be 7 or 8 slots, and of course this meant that the coil ends must overlap. The example here is a PM motor with 36 slots and 8 poles, and it shows a single coil with a span of 4 slot pitches. The advantage of having a large number of slots per pole is that the windings can be spread out or distributed instead of being concentrated at particular locations around the bore of the stator. This has several advantages. On the one hand, the distribution of coils reduces the lower order spatial harmonic effects and makes everything smoother and closer to a sine wave, while reducing torque ripple. Distributed windings can use smaller, more manageable wire sizes, and they have better heat transfer to the surrounding laminations. Then in the 1980s or even the 1970s, along comes the brushless permanent magnet motor, and to cut a long story short, the rapid take-up of single-tooth windings, that is, windings with a span of only 1 slot pitch. Some of these windings are non-overlapping, and of course the bulk of the end windings is greatly reduced. This helps to reduce the overall length and the copper losses while improving the efficiency. The number of slots per pole is, of course, fractional, and 1.5 was a prominent number, for example, in a 12-slot 8-pole machine. The example here has 12 slots and 10 poles, 1.2 slots per pole, with single-tooth windings. The working harmonic is the 5th spatial harmonic with 10 poles, that is P equals 5 pole pairs. In the next slide, we can see that the winding produces space harmonic fluxes as well, and here we can see a subharmonic with P equals 1, only 2 poles. It goes straight across the rotor from one side to the other. The presence of these subharmonics is often ignored in textbooks, and it's unusual to see a diagram like this. The concept of single-tooth windings with slots per pole close to 1 is well over 100 years old, but it works best in machines with larger numbers of poles, which implies higher frequencies. Therefore, in larger sizes, there would have been trouble with core losses because of the higher frequencies involved. Of course, in the old days, inverters were not widely available as they are today, and the question didn't really arise. Now, I would like to take a look at all this from an idealized theoretical point of view. Here we see the magnetic field produced by a sinusoidally distributed current sheet winding here in the middle. The current flows in the axial direction, and it is sinusoidally distributed around the circumference of the winding with 2 poles. There are no end effects, no slots, no salient poles, and no magnets. There is also no iron. So the field spreads out, and it is not confined to a magnetic core. Outside the winding, it attenuates as 1 over r squared, where r is the radial coordinate. Inside the winding, it attenuates as 1 over r to the power 0, which means no attenuation at all. The interior field is uniform. We can see not only the flux lines, but also the equipotentials. which intersect the flux lines orthogonally, forming so-called curvilinear squares. These figures were produced analytically, and it is unusual nowadays in finite element calculations to see the equipotentials. They're not really necessary, and in saturable materials with complex boundaries, the orthogonality is lost, and the picture would become messy if we plotted both sets of lines. So here is the simpler picture of just the flux lines, two-pole and completely air-cored. Now suppose we introduce an infinitely permeable iron core inside the winding and just touching it. The field remains uniform inside, but it doubles in strength. Why only a doubling when the permeability is so high? The iron core relieves the need for magnetizing force H in only half the magnetic circuit, the part on the inside, hence the doubling. This sounds casual, but in fact it's mathematically rigorous. Next we see an infinitely permeable iron core surrounding the winding with air inside. Again the field inside remains uniform, while again it doubles in value. The big difference this time is that the flux is confined to the stator core. It no longer spreads out through the surrounding space. Finally, we have iron cores both inside and outside. The field is 15 to 20 times what it was in the purely air-cored case. Why not more? The answer is the air gap. With infinitely permeable cores or cores of very high permeability, the air gap absorbs almost all the magnetizing force of the winding, the H required to produce a given flux density B. In an induction motor, this H must be supplied by the ampere conductors of the stator winding. Now let us go through the sequence with a four-pole winding, P equals 2. Here it is, purely air-cored with both the flux lines and the equipotentials. And in the next slide we see just the flux lines. The interior field is no longer uniform. It decays on the inside with R, while on the outside with 1 over R cubed. Thus on the outside we see a much more rapid attenuation than in the two-pole case. On the inside, the flux density at the axis is 0. Next we see the sequence with an iron-cored rotor, an iron-cored stator, and finally with both rotor and stator cores. Again, the flux is confined to the stator core. But now it is divided into 4 packets instead of 2, and accordingly in the circumferential direction, the cores are carrying only half as much flux as in the two-pole case. Therefore, the radial thickness of the cores can be reduced. On the stator, this is good for heat transfer, while on the rotor it makes space available for the shaft, which is not laminated and may have poor magnetic properties, so it is as well to keep it away from high flux densities. On the other hand, the number of ampere conductors available to drive the flux across 2 air gaps is only half what it was in the two-pole case. To maintain the same flux density levels, the magnetizing current has to increase, and this is one reason why the power factor of induction motors tends to decrease as the pole number increases. We can also imagine that in a real motor, the end windings are much less bulky than in the two-pole motor because the coil span is only half. Of course, with twice the number of poles, the speed will be halved if the frequency remains the same. Nowadays, inverters are often used to supply frequencies higher than 50 or 60 Hz, so there is no problem getting a 4-pole AC motor to run at 3000 or 3600 revs per minute or even higher. For variable speed drives, this is a good solution with high power density. The story continues with 6 poles, flux lines and equipotentials, and with 12 poles. Notice how the flux-free zone appears in the center of the rotor as the pole number increases. Also, the attenuation on the outside is very rapid, and the field is confined to a narrower and narrower annulus. In very large machines, the center can be left out of the rotor, not completely, but replaced by a spoked structure like a cartwheel to reduce weight and inertia. Field configurations like these are sometimes magnetized with Halbach arrays to reduce the need for magnetic iron and to reduce the spatial harmonics in the flux distribution. Finally, let's put them all together with the addition of a 24-pole machine at bottom right. All these machines have iron cored rotors and stators. Now, all the arguments we've made up to here continue to hold throughout this series. We can see the effect on the ratio of rotor and stator diameters, the so-called split ratio. With a larger pole number, the stator yoke can become radially thinner, so the rotor diameter can be increased with the same flux densities, and this provides a natural increase in torque. This is exploited in automotive brushless PM traction motors, for example, where 8 or more poles is not uncommon, in spite of the high speeds, 6000 revs per minute and more, and the need for high efficiency. Now, we might think that these theoretical models are too idealized to be of much practical use, although we have certainly drawn some practical lessons from them. But we can take it further by recognizing that real windings, distributed in discrete numbers of slots, can be analyzed by Fourier series into a set of sign-distributed windings with an ordered succession of pole numbers. This harmonic analysis of winding distributions is, of course, fundamental in AC machine theory. It is the basis of differential leakage reactance and of cusps in the torque-speed curve of induction machines. It is convenient and quite rigorous to imagine a real winding being resolved or decomposed into a set of windings with different pole numbers, as in this figure. They can even be superimposed in the equivalent circuit. Another feature of these windings is that the inductances, both self and mutual, become smaller as the pole number increases. It's an interesting question to study the mathematical effect. Does the inductance go with 1 over p or 1 over p squared or some other function? The answer can be found in the good textbooks for both synchronous and asynchronous machines. But instead of stating a definite answer, I'm going to make a less common statement, that the answer is different for the actual inductance in henries and the per unit inductance. The per unit inductance depends on the normalization bases for the voltage and the current, and these both change with scale and pole number and with the number of turns. In some ways, the per unit inductance is more fundamental than the actual value in henries, because it is independent of the number of turns and the voltage level, and so it characterizes the inherent inductivity of the machine, not just a particular value at one voltage with a particular number of turns. So we can say immediately that this machine at bottom right with 24 poles will have a lower per unit inductance than this one with 2 poles. And this affects the entire behavioral characteristics of these machines. Now let's take a look at this family of electric machines. We've seen this before. It's my classification of electric machines with classical machines on the left and electronically commutated or inverter-fed PM and reluctance machines on the right. Just looking at this, we can recognize some familiar combinations. For example, the wound field synchronous machine with 4 poles is common as an industrial scale generator up to a few megawatts. The 4-pole synchronous reluctance motor is commonly put forward as the best for synchronous reluctance motors. The commutator motors are both 2-pole, the commonest pole number for small mass-produced commutator motors. The induction motor seems to have the proportions of an 8-pole motor in terms of its diameter ratio, but possibly not enough slots. The diagram is missing some of the most important 12-slot 8-pole and 12-slot 10-pole PM brushless AC motors, but at least it shows the IPM, the interior permanent magnet motor, with 4 poles, and this machine would have a distributed winding, not a single tooth winding. As for the switched reluctance motor, well, it is not widely known that this was one of the first machines, possibly the very first, to exploit the concept of the single tooth winding back in the 1970s before the brushless PM motor burst on the scene. The number of poles appears to be different on the rotor and stator, but this conundrum is resolved when we consider the magnetic flux pattern, which has a definite number of poles and links the rotor and stator poles in what is called a vernier fashion. I have not mentioned pole changing windings, which of course are used for speed changing, and I haven't mentioned linear machines, where some of the rules go out of the window. In rotary machines we have only 2 pi radians to work with, but in linear machines there is no such limit. But that does not allow us to escape from the constraining relationship between speed and frequency and pole number or pole pitch, or indeed from the effects of winding harmonics. To finish, here is a rather philosophical reflection. This is a common diagram representing Park's reference frame transformation, the DQ axis transformation for synchronous machines. Similar and related transformations are used with induction machines and DC machines. Do these transformations change the number of poles? No, they don't, but they often hide the number of poles by working in electrical degrees. What they do is to change the apparent numbers of phases, and certainly they alter the apparent motion of the coils by casting them in different reference frames, which may be rotating or stationary. So what I want to say is that highly theoretical analysis by these methods can sometimes take our focus away from the important fundamental influence of the pole number, which is so important to the designer. Here's my bio and references, and thank you for listening.